Okay. All right, so let's get started. And so we're grading homework 2. There was an issue from the graders, so the grades are a little bit late, but we're trying to work on those. We have around 70% graded, so I have 30% to go. Also planning to release homework 3 grades at the end of this week, since it's much shorter than the previous homeworks. We're able to notice that some people are starting the homeworks late, and it's easy to tell. Those who started late especially struggled with homework 3 because there was less guidance than homework 1 and 2. So we recommend that you start early homework 4. It's much more difficult than previous ones. Yeah, there was also some questions that were missed by the majority, so it's probably because something was not explained well, or maybe we gave a false hint in office hours. So we try to be lenient with those. And today is going to be just showing you a few examples or algorithms to solve reinforcement learning. I assume you're all gone through the notions we have introduced last Monday. I'm not going to explain those again. And we're going to talk about the value iteration, policy, where we learn the value functions, policy iteration, where we learn the policy. And at the end, I'll be explaining deep Q learning, just the logic behind it, and show you some examples. And so basically in the homework 5, we'll be doing Q learning, just using the tabular one, so no deep learning involved. And the second part will be some deep learning, but the environment is really simple. So it should be converging in the deep learning case after like 1 hour or 2 hours of training. Usually it takes days. Okay. All right. We'll be working again on Markov decision process, and S state space, A action space, and R is the reward for transition, and P is the transition kernel or probabilities. And we'll be assuming in the algorithms that I'll be showing you, this is deterministic. So once you take an action, there's only one state that you'll be transitioning to, not random states. Okay? And in all cases, we're trying to learn a policy that will maximize the accumulated or expected accumulated rewards, and gamma is the discount rate that is lower than 1 and greater than 0. Okay. We already introduced the V, the state value function, and Q, which is the state action value function. It's basically the etap I, but we condition on the initial state. And in Q, we condition on the initial state and action. Okay. Last thing we mentioned last time, it was the what you call Bellman equations, and that's basically what you call recursive. No, it's more like a dynamic programming. Okay. Because there's a relationship between the Q as SA and Q at the next state, okay? And here there's a factor gamma, all right? So for V, we can also write the same thing. We can write that V of S is equal to RS S prime plus gamma V of S prime. So you can see here that we have something like F equals R plus gamma of F, okay? Equals R plus gamma of S prime, okay? So this dependence relationship is what we're going to use later to define some properties. We're going to go back to that later. But the trick here is that if we learn V, we can learn Q as well, okay? And once we learn Q, then the best action, or basically PS, I'll call it star, is the argmax over the actions of QSA, okay? And this definition we define here, this is what we call the greedy policy, okay? We're just trying to maximize. Once we have Q, we take the argmax of the, with respect to the action, and we define the Q policy. So once we define the Q policy, or sorry, the greedy policy, okay? So with the greedy policy, we say that P of S is the argmax with regard of A of QSA. So if you use this notation, then we're going to have that QP, using this policy here, of SA is equal to the reward plus gamma max over A of QS prime A. Okay? Remember this very well, okay? We're going to go back to it. So last time when we were filling that environment with the value function values at different states, there was this intuition that we're basically doing some recursion, and then once we fill that, we just be following the gradient or the direction where we have the maximal value function. And that's basically what the value iteration does. We'll be learning V immediately, and that's exactly what we were doing last time, okay? So we can start from any initial value function V, or we can initialize it with 0. Then we can go through the different states and then the different actions. And for each of these tuple that we're getting here, SA, we take action A at state S, and then we are getting the reward R of SA. Okay? Once we do that, I forgot factors gamma here. Once we do that, we just update our Q. You're saying, well, we didn't initialize Q. Well, we don't need to, because in this case, we only need Q in this for, so let's say we have 4 actions like this, the toy environment. So we only have QS of up, right, down, and left. Okay? We don't need to store QSA for all tuples. We only need it for the actions that we have here. Okay? Once we do that, we update our value function that was initialized before to the maximum over the actions. So we said before that VS is basically the sum over the probabilities or the policy, the weights that we are going to give the action A. And this is the eta of pi starting with S0 equal S. Okay? And here, since we are using the greedy policy, we are taking A, which is the argmax, again. We're just going to note it greedy, okay, to make it short. We said that for greedy, we're just taking the argmax, so it means that for the policy of greedy up, okay, I'm just going to do clockwise, left, up, right, down, okay. So let's say the argmax is left, so it means that these probabilities are going to be 1, 0, 0, 0. Okay? So this sum here simplifies simply to the max over QSA. Okay? I'm giving weights 0. Okay? So if we remove all of this, this is simply Q of the greedy policy of SA. So once we looped through all the states and through all the actions, we're just gonna return the greedy policy at the final iteration. We call this asynchronous. Why we call it asynchronous? Because we are updating VS for each state. We're going to see the synchronous variation. For the memory space, we need to store the policy, which is the size of the state space. And we have to store V, which has the same size. And we need to store these quantities for each action, so that will be the size of the action space. And for the computations, we're just doing for each state, we're doing A operations, okay? We're storing A here, and we're taking the max over A. It's going to be S squared in non-deterministic. Why? Because instead of Vs prime, we're going to have the sum over the transition probabilities of S prime SA V S prime. So there we're going to have, for each S, we're going to have S operations, so it's going to be S squared. But for the deterministic one, we're going to only have a constant number of computations. Okay. For the synchronous one, we're not updating at each state. We are updating V at the end of each round, okay? So previously, this equation was basically under Q, was inside this loop that we have here, okay? For the synchronous one, we're going to explore the environment, update Q at all states, and then go back to V and store the max over the action space. So in this case, we have also to store Q for each tuple SA, okay? So in this case, we're going to have more memory space taken by Q, and also, just more memory space by Q. We can reduce it. Instead of storing Q, we can store another value function V prime. Yeah, the computer change here is the same. We're just saying we're going to add more state space for Q. But we can do it without using Q, but instead using a secondary value function, okay? So we're going to do the synchronous one, asynchronous one, but on V prime. And at the end, oops, I'm going to remove this. Okay. And at the end, I'm going to append that new learned V prime to V, okay? So the updates are using V, but I'm storing my maximum at V prime. And once I go through all the states, that's where I update my initial value function, okay? I'm going to show you examples of these so you don't get lost in all these concepts and what's the difference between the two, okay? The good thing about value iteration algorithms is that we have some guarantees. First guarantee is that if we visit each state infinitely often, then we can get that V converges to the optimal V star. By infinitely often, it means that at each round, the probability of visiting any state is not zero, basically. If I pick any state and any round, the probability of frequenting that state is not zero, okay? The other advantage is that if we choose the greedy policy, we can converge faster than V converges. We're going to see this why, but the concept here is that if I am in a certain state here, let's take this simple example, okay? We have 3 cells. I'm at state S0, this is S1, this is S2. Now let's say that the optimum one is S1, okay? So for V, I need more time for V to converge to the real value function, okay? But for P greedy, I don't need this convergence. I just need to reach the stage where V of S1 is greater than V S2. Okay? Means the greedy policy does not care about the value, it just cares about the order. Okay? So once V S1 is greater than V S2, the greedy policy converged. But for V, it still needs more time to converge to the exact value at that state. The third one is if I can bound the difference between my current value function and the next one, then I can also bound the difference or the difference between the new update and the optimal V. All right? So let's say if I know that gamma is equal to 1 over 2, so this is basically becomes 2 epsilon. And if I reach the stage where my new V prime minus V is less than 0.01, then I know that this bound is less than 2, basically 0.02. Yes? The discount rate, yeah. So if I choose a discount rate of 1 over 2, if I can find a bound on the maximum or the upper bound on the difference between the old value function and the new one, I can estimate the bound between my new update and the optimal function. All right. So why is this important? Well, I'm just going to use the same example again. So let's say I reach a state where I'm in this position, either go up or left, okay? And I find the value function here is 0.5. The value function here is 0.4. And the value function here is 0.3. So if I reach the case where I have the bound here is 0.1 and the bound here is 0.2, then I don't have to train more. Okay? Why? Because I know that the optimal value function will be actually between 0.48 and 0.52. Okay? And here's the same thing. I can guarantee that it's between 0.38 and 0.42. So it doesn't matter what the true value or the optimal policy. I'm sure that I'm going to get a larger optimal value if I go up. Okay? So this stopping criterion will save you a lot of time. Because let's say you're just saying that once the difference between these two is greater than this bound, then I don't have to care about updating value function anymore. Okay? All right. Yeah, before moving to policy iteration, I'm going to show you some examples and also answer some questions from last time. Any questions so far? Okay. I don't know why it restarted, but anyway. Okay, let's get started here. All right, so here I'm just defining the environment matrix. And 4 by 6, I put -2 in the red cells, which is the wall, and 1 for the reward, and -1 for the penalty. Okay. Here I'm just defining my action space.
Is it possible for you to zoom in a little bit?
Like this? Okay. Yeah, this is the environment from last time. I'm just putting 1 for the target, -1 for the penalty, and -2 for the wall. Okay? And I'm defining here a function called next. So what this does, it just makes sure I am staying inside the boundary. I'm not going outside the limits of the matrix here. I use gamma 1/2, initialize the value function, just the value function where everything is 0, and the policy, the same thing. Okay? So the action is here, 0 for left, 0 for left, 1 for up, so clockwise. Left, up, down, right, and then down, okay? So what I do here is that I'm just using itertools for product. I'm creating all the possible tuples for the indices ij, which is the coordinate of the states. And I'm initializing my a certain queue where I'm going to store the updates for each action, okay? So I'm avoiding these positions, which is either the target or the penalty or the wall. I cannot access those states, okay? So at my initial update, this is the synchronous one. Sorry, this is the asynchronous one where I'm updating for each state. This is the first iteration that I get, okay? So the first iteration, I explore the environment. The only position where I get a reward 1 is in position 4-3, which is in this case 0-4, and that's where I'm going right, see? So this is I'm going right, and in these two positions, I need to go basically up to get to that position, okay? If I continue at this update, I'm just gonna repeat this. It gets filled, which is exactly what we did last time. Okay? This is the last iteration. Now nothing is going to change. And here we see the optimum policy, right? Up, until we reach the target. If you remember last time, this value here was 1. Okay, so it was 2 to the power of -7, if I'm not mistaken. Sorry, exponential. So there's 0.5 to the power of 7. Yeah. So last time we found that it was gamma to the power of 7, and this is exactly the value we get here. All right. So in each state, we're just going to try to go to the next one that has a larger value function. All right. So what happens here is that I'm going through each iteration. I'm starting from the initial one with zeros, and I update the value function 1 position at a time, okay? So here in the updates, I start from this position, okay? So I'm going here, I'm going up left, up and right. I find that the rewards are still 0, so I'm going to get zeros, and I'm going basically iterating through all the states, I think, yeah, this way, all right? So it's column-wise, and I'm moving in this direction. Now, if we do the asynchronous one, so in the asynchronous one, we keep a copy of our value function at the beginning. I'm calling it vnew. I am doing the updates queue, but I'm only saving them in vnew, okay? So queue here still depends on the old value function. I'm not using the new one, okay? In the last method, which is the asynchronous one, v and vnew are the same, okay? So when I'm updating v at each state, this will affect also my next states, okay? In this case, I'm decoupling those. I'm updating the entire, I'm updating the entire value function, and then I'm doing the updates at the end. Practically, if you run it just this simple way, it's not going to give you any difference, okay? Except here that we're getting basically slightly, let me initialize it by 0. So here, you're not going to get any advantage over the asynchronous one. Why? Well, because we're just updating from this direction, all right? So this one will be the last one to update. Let's do it the other way, which is I'm going to reverse the order of the updates. It means that once I explore the environment, I'm going to update this region, then this region, then this region, okay? So it means I'm updating state 03 after I update state 04. Okay. Yeah. So here it's not making any difference. If I go back to the initial method and I do the same thing, oops, it fills out immediately. Okay, so I'm going to do it again. Only one iteration, and it fills out almost immediately. Okay? So the difference is always here. When I'm updating V, I update one state after the other. In the second one, which is the asynchronous one, I'm updating all states once. Okay? I update 04, then 03, then 02 based on the previous estimate. In the other in the initial case or the first case where everything fills out at the same time, I fill 03 after I updated 04, and I update 02 after I filled 03. Any questions? Okay. So this is the difference between synchronous and asynchronous. If you get lucky, or if you know the right order, basically if you start from the last state that allows you to reach the goal and then update back, then you get faster convergence.
Why are the terminal states both have value 0 when you do the iterations? Like, why don't they stay there?
Because we can't reach those. Okay, so what happens there is that we don't reach those. Okay, so SP, which is the next state, is never 05 or 15. Because once we reach this, once the next state is 05, we finish the game. Okay? Yeah, so this is what I'm doing here. If the current state is -2, -1, or 1, which is basically these cells here, I don't do the update. Because those states, I cannot access them, okay? So one question last time was, well, what if I have one here? What's going to happen? Let's do that. And update my environment. So this is my new environment. Now let's do the synchronous one. And there you go. Let me just run it one more time. There you go. Yeah, I'll scroll down. Yeah. So what happens is that if I am in the lower half, I'm going to go to the new target here. If I am in the upper half, I'm going to go there. And you can check that what's happening here is basically I'm taking the environment where I only have the top, and I'm taking the environment where I only have the bottom, and I'm taking the maximum of the two. Okay? Let's see this. Let me, for example, remove the initial target. I'm just going to keep the second one. This is my new environment. There you go. All right. So when we had both, it was 1.5, and here it's 1.5 in the bottom, and you can check that when I combine both, it's just the maximum over the value functions of both environments. Okay. So it's kind of additive, but using the maximum. All right, let's go back to some theory. Okay. In policy iteration, we're trying to learn the policy directly, because I forgot here a symbol of LaTeX, which should be pi there. I'm initializing the policy, but also I'm initializing V. And this is the tricky part about policy iteration, is that you also have to estimate V, which is different in, for example, if you're learning Q, that's all you need. You don't need other quantities, okay? But in policy iteration, you always have to keep an estimate of the value functions. Otherwise, you'll need to sample all possible states, all possible actions, and build your own V estimate at each round, which is quite expensive, okay? So once we do that, we try to solve this system, okay, which is basically learning V, because we know that the V function satisfies this equation. All right? So at each round, we go through the states and the actions, and we build in this system of equations. Okay. So here it's Vs prime. Okay. All right. So we're building a linear system, and then we're trying to use that V, this is basically argmax over A of Q S A. Okay? And this is the expensive part. To solve this system is not easy. Even if you have like 5,000, 6,000 states, that can be a lot compared to the previous method. Okay. The advantage, the good news is we don't really need to solve the equation. And that comes from what we call Bellman operator. Okay? So you can look at V, and V is just a function from the state space to R, which basically it gives you a scalar at each state. And I use G here, which is a function of the policy and the transition probabilities. Okay? But let's not think about it. So if I take this operator, we can show that if I take a function, f, and I apply tf, and I call this like f1, and then I apply tf1, I call this f2, and vice versa, then I can show that fn will converge to an f star that verifies this. Okay? It means that by just applying the operator without solving the linear equations, I'm just going to apply the Bellman operator like 10 times, 20 times, I'm going to converge to the solution of the equation that I had before, which is this. Okay? Means if I start from a random value function, you can initialize it with zeros, and you run this update multiple times. Okay? Practically what this means, it means that for all the states, I'm just going to do Vt plus 1 of S is going to take R SS prime plus gamma of my current estimate at S prime. All right. So if I start from a random value function and run this update multiple times, I'm going to converge to the solution of the linear equation that I had before. This is a classical proof. The first argument that we use is that to show that the operator T is a contraction. And we call H a contraction if the distance between the image of two elements is less than the distance than less than the distance between the two elements. Okay, so distance between the images is less than the distance between the elements themselves. Okay, so why do we like this? Well, one way is that I can show that hn of x, which is h applied n times to x, minus hm of x, like this, is going to be lower than some function of alpha. I'm going to call it like delta of alpha of x minus y. And as the difference n plus m goes to infinity, I'm going to have that the difference between the images goes to 0. Sorry. Any questions? No? Okay. So I'm saying here is that hn(x) will converge to h star of x as n goes to infinity. All right. So if I substitute in here, I'm going to have h star of x minus hm of x is lower than some delta of alpha. And here is going to be, okay, so the bound here goes to infinity. If the difference goes to infinity, this goes to 0. So basically, sorry, I'm going to remove this. Oops. So this goes to 0 as m goes to infinity. Okay. If you want the bound, the realistic bound, it's going to be h star of x minus n of x is less than 1 minus gamma. And here is going to be gamma of n, if I'm not mistaken. And this is going to be some bound of h star minus h0. So in our case, alpha is equal to gamma, and here we're dividing by gamma. And this also goes back to the initial argument we made last time, that we want gamma to be strictly less than 1. Practically, you don't want it to be equal 1, because any policy that reaches the target, it doesn't matter the horizon that you will take to reach that target, it still gives you the same reward. So we introduce the discount rate. But we find also that we want discount rate less than 1 to have these guarantees that we are getting with the Bellman operator. So it has also analytical motivation behind that bound. All right. So I have 12 minutes left. I'm going to kind of skim through the deep learning case, and it's the same logic that we had before. The only problem here is that we have possibly an infinite number of states. So we can store Q, we can store V, and so let's say you have 1,000 actions around 1 million states. That's going to be, Q is going to take like 1 billion the size of floats. That's a lot. You need probably more than 120 gigabytes of RAM for that one. Okay. The same thing in policy iteration. We cannot hope to solve the system because you're going to have a large number of equations in the system. So the solution here is the same thing we have done in supervised learning. Okay. We can use classifiers for policy, and we can use regressions for V and Q. Okay. So P here is going to map the state to the actions if we have a finite number of actions. And the regressions here are going to map the states to the values, or the states and actions to the values. And the guarantees that we had before will not hold all the time, depending on the hypothesis class that we use. There are previous papers that assume that if you use V and Q as linear regressions, then you can have some certain guarantees. And if you use like Q, the same thing, you can have like logistic regression for Q, then you can have some guarantees on the convergence. But generally, there's not, you can't say much about the convergence in this case, especially if you use deep learning with the neural networks. We don't have any general bounds for that. So it's the same logic as before. We have two constraints. One thing is that the state space is too large, so we have to keep track of larger size of samples. That's what we call the replay memory. And the second thing, which is that you want to make sure that when you update the policy, you don't converge to a local optima. Because let's say I have a very large grid and I'm moving around, then I found a target that has a reward +1. So if I'm not careful with the convergence, yeah, it's not that, I'm gonna go back to that one later. So if I'm not careful with the convergence, I might just converge to the policy that will just take the first reward that I get. Imagine I have second reward that has value 10. So if the convergence is too fast, I will just be satisfied with my first reward that has 1, and I will ignore others that might have a value 10, okay? So that's why we introduce a parameter that's called epsilon, okay? So initially, we can start with value 1, and at each step, we're going to sample a random variable, uniform between 0 and 1. If epsilon is greater than that random pick, then we're going to pick a random action, and otherwise, we're going to pick the greedy action, which is the one that follows the Q policy, okay? And this goes back to a problem in reinforcement learning called exploration and exploitation. Explore, exploit. So how much are you willing to explore the environment before you start converging to or updating Q? Or how interested are you in just finding something that works and you're not interested in exploring everything? Okay? Okay, so we explored the environment using this policy. We call it epsilon greedy, which is like greedy with probability epsilon, basically. We store the samples that we get, and after a while, we take a batch from that replay memory, and we minimize this loss. Why we minimize this loss? Because this is basically here, it's TQ. It's the Bellman operator applied to Q, and this is my Q, okay? And I'm trying to minimize this error. Because if I converge to the case where TQ equal Q, then I know that I converge to the optimal Q. The optimal Q will verify this equation, so I'm trying to minimize this loss over the batch. Okay? And at the end of each episode, or at the end of each episode, I'm going to decay epsilon. Usually you decay it either linearly or exponentially. Usually it's linear. You do like epsilon equals, so it's going to just be epsilon takes epsilon minus something, let's say minus alpha, but then you make sure that this is at least maximum between this and some upper bound, usually like 0.1 or 0.2. I mean, these are hyperparameters, so it depends on the environment you have, the size of the neural network, and other things. And at the end, you return the greedy policy associated with Q. Okay? Theta here is the parameter of the model. In a linear regression, it will be the weights and the bias. In a neural network, it will be the weights of the different layers in the neural network. Okay? And the original paper uses the square root, the mean squared error, and practically it's not stable. So they use another loss called Hubert loss, which is basically square root when you are far from 1. If the error is larger than 1, you're just doing mean squared error. But once you get closer to, once you get closer to 0, you're using mean square error. But once you're far from 1, you are using the absolute error. Okay? So in that case, the gradient will be either -1 or +1. But once you get closer to 0, the gradient will shrink. You try to shrink the gradient there to get more stable conversions. Okay? I'm giving you a lot of hints for homework, so keep track of these. Yeah, I'm going to show you some examples from the next homework, as well as something from a paper back in 2013, which basically proved that deep reinforcement learning actually works. Because before that, there was this complaint that reinforcement learning is interesting, but once you use neural networks, no one managed to get a model to basically learn something that's complicated. But with the deep Q learning and all these tricks that I mentioned about the memory replay memory, the loss, the decaying, all these tricks, when combined together, they can allow you to get something that converges, actually. So I've just Googled deep Q learning. The original author of that paper actually now at DeepMind, so it should be here. You can find some examples, and most of the papers will use simulations because you can't use real robots to do all these experiments. Some of the famous ones is the Atari games, which is basically playing games like Breakout and other stuff like that. I'm gonna let you watch this one. So this is a random. We start from one random policy. If you train this model, you see that initially it starts detecting that the edges are more, you get more chance if you just stick to the edges. But more and more, you start playing the game like a normal human being. But we said that with the discount rate, we also want the policy not just to finish the game, but to finish the game as early as possible. Yeah, and this is where the agent will learn tricks to accelerate the game. So in this case, it will try to get rid of the blocks at the edges and then just hit as many blocks as possible. It's way difficult than it looks if you want to do it yourself, because you're going to save hundreds of thousands of samples before you reach anything significant, and you have to tweak the decay rate and the learning rate, and all of those depend on the game. So if you change the game, you also have to figure out, well, what's the best decay rate for this environment? What's the best learning rate for this environment? Yeah, my experience, this is very difficult to train. And the reason is you get some randomness in the environment, and you get some penalties or some rewards. And yeah, the actions from the adversary is also random. So this game was very challenging to train. But for our homework, we'll just be doing something very simple. We'll be starting with this environment. You start from initial position there. You're trying to reach the target, but then the target will move randomly. So for the tabular one that we showed at the beginning of the lecture, we're just going to try to reach the target. That's it. Once you reach it, it's done. Yeah, this is a random policy. It means like going up with probably 25%, right? 25%. Yeah, Yep, and you hope to reach out. Come on, okay, did it. And during the training, you're gonna do something like this. I mean, sometimes you get it right, sometimes not. You can get sometimes some local corners where you just get stuck. And yeah, the conversions will look something like this one. So yeah, at the end of homework 5, you can do this kind of tricks. You're not going to teach it, well, if it is at the right side, go to the right, or if it's left to the right, the left, you just implement your Q-learning and leave it interactive environment, and it will learn. Yeah. So in this case, so usually in that case, you don't want to really follow the greedy policy. You want to add some randomness. Because you see in that case, when you use deep learning, you can get where case is just going up and down, up and down. So you want to add some little randomness to leave that, that area, or basically that you don't get stuck. All right, any questions? Yeah. So tomorrow I'm holding 2 office hours. If you're stuck with homework 4, come to the office hours. And I'm sure many of you will be.
Everybody else will be running in like an hour. I'll be running in 3.
Yeah.
The first problem? That wasn't too bad. Oh my God. I'm really surprised.